All right, we want to do just a little example for loads at an angle on our truss. Very straightforward because we've covered this already. We have a 12 kilonewton load at a 65-degree angle to the x-axis, so this is downward to the right. So we have a downward to the right components, and the vertical one is going to be 12 sine 65, the horizontal one is 12 cosine 65. So for this same problem that we've just done, now your homework is to find the reactions. So find the reactions and draw the final free body diagram. So go ahead and pause the video and do this one. All right, so we have our lines of action of the forces, and if we're going to take moments about A, then I'm going to look at the other forces. I have a line of action there, a line of action there. This 3 kilonewton is the same, and line of action there. So we're going to, so we take moments about these points, and then we need to get the moment arms, and we need to take, the forces times the moment arms and get the correct sign. So it's going to be 5.07 times this distance, which is 5 meters. And we have 10.9 times this distance, which is 6 meters. And we have by times this distance, which is 12 meters. And we have 3 kilonewtons times this distance, which again is 6 meters. And when we look at the signs, taking about A, the 5 goes this way, which is clockwise, so it's positive. Positive. The 10.9 goes clockwise, which also is positive. The 3 goes counterclockwise, so it's negative. The by goes counterclockwise, so it's negative. Solve that, we get by is 6.05 kilonewtons. Now we're going to take moments about B. So we're going to take moments about this point, and we now have the AY times 12. We have the 5.07 times 5. We have the 10.9 times 6. And we have the 3 times 6. For the signs, oh, then notice the AX goes right through the point, so it's 0, we don't even consider it. So what is the sign for the AY? It's positive, it's clockwise, so it's positive. For the 3, it's also clockwise, so it's positive. For the 5.07, it's also clockwise, so it's positive. The 10.9 is counterclockwise, so it's negative. Solve that, we get 1.82. And we take the sum of the forces in the x direction. To get AX, I only have 5.07 and the AX. They're both going to the right, so they are both positive. And I solve for that, I get negative 5.07 for AX. So our final free body diagram, that was positive, so we don't change the arrow. That was positive, so we don't change the arrow. This one was negative, so we flip the arrow around and it goes to the left. We can do our check. What do we see? Up and down are equal. Right and left, it's not a real check, but it's, we want to make sure that we can look at the figure and find that what's going to the right is equal to what's going to the left, and those are also equal. Okay, so here's another problem. Find the reactions for this one. Okay, pause the video. And I have two loads, both are at an angle, so I use the components. 10 cosine 75, 10 sine 75, 8 cosine 60, 8 sine 60. I can notice both angles are with respect to the x-axis, so I can use those angles directly. I get these values. This is downward to the right, so I have downward to the right. This is upward to the right, so I have upward to the right. The cosine of the angle components go in the horizontal direction. The sine of the angle components go in the vertical direction. So I'm now going to work from this free body diagram. I have a pin at A, so I have an AY and an AX. I have a roller at E, and of course that roller is horizontal, or I have a horizontal force there because of the way the roller is set. And so we have our equations. I'm going to take the sum of the moments about A equals 0. And in this particular case, I did not draw the lines of action, so hopefully you're getting used to doing this. So I'm taking moments about A. Notice that line of action goes through point A, so I don't need to consider that 2.59 kips. This is going to be 9.66 times this distance, which is 10. This is going to be 6.92 times that distance, which is 5. This is going to be 4 kips times that distance, which is 5. And then we have EX times this distance, which is 10. There, the signs, taking moments about A, so that's going to be clockwise, so it's positive. Counterclockwise, so it's negative. Counterclockwise, so it's negative. And then counterclockwise, so it's negative. So those three are negative, and the first one is positive. So I solved that for EX, I get 4.2 kips. I'm going to take moments about E. We have AX times 10. The AY goes through the point, so I don't, the line of action of AY goes through the point, so I don't consider it. I have 2.59 times 10. Got 9.66 times 10. I've got 6.92 times 5. I've got 4 times 5. They're all written here. How do I get the signs? This one is clockwise, so it's positive. So I'm taking moments about E. That's going to be clockwise, so it's positive. The 2.59 also is going to be clockwise, so it's positive. The 9.66 is clockwise, so it's positive. The 6.92 is counterclockwise, so it's negative. And the 4 kips is clockwise, so it's positive. So those are all the signs. I solve that, I get AX is equal to negative 10.79. And I'm going to take the sum of the forces in the y direction equals 0. So I have AY, the 6.92 is upward, so it's positive. The 9.66 is downward, so it's negative. And I solve for AY, I get that. Reverse the arrow for that one. Those arrows don't change. And this is my final free body diagram right there. Okay, here's a case where the roller is neither in the X or Y direction. So how do we handle that? So I have a pin here, and now I have a roller there, but that roller is at an angle. And how do we handle that situation without changing our coordinate system? So we're just going to keep it the same. Yes, you could change the coordinate system, but no, we're not going to do that. I'm going to show you a different method, and that way we always have. I'm going to establish. We're always going to use, well, until we get to the very end of this class, X and Y like that, and so I know that because the roller is at that angle, well, my roller force is going to be perpendicular to that. So that's the direction of the roller force. I need to figure out what that angle is with respect to our x-axis. So I need to know what this angle is. I'll call it beta. How do I get that? Well, I can create this triangle here that looks like that. I'm going to call this force at C, I'm going to call it C perpendicular. So that's the unknown force. I know that I'm going to call this angle here theta, that angle beta. This is a right angle. And so I can figure out what theta is. So here's theta, and theta is this angle here also. So in other words, that's theta, this is theta, and this theta, we can see that the tangent of theta is that distance over that distance, and that those two distances are this one is 4 and this one is 6. So the arctangent of 4 over 6 gives me 33.7 for theta, and beta is going to be 90 minus theta, right, because this is a right triangle. So beta is 90 minus theta, so that makes beta 56.3 degrees. So that means that with respect to the x-axis, C perpendicular is 56.3 degrees. So we're going to use the cosine of 56.3 and the sine of 56.3. So the sine of 56.3 is 0.832. The cosine of 56.3 is 0.553. So I'm going to replace this C perpendicular with these two forces, two components. This is upward to the left, so I'm going to have upward to the left, and so this is going to be the sine of the angle, 0.832 C perpendicular. This is going to be the cosine of the angle, 0.553 C perpendicular. We've done these a bunch of times, so I'm not going to dwell on that. That's going to be 5 sine 45. This is going to be 5 cosine 45. This is 7 sine 50. This is 7 cosine 50. And now we have our initial free body diagram. We put on our usual AY and AX because that's a pin, and I now can use this free body diagram to solve for my unknowns, the three of them being C perpendicular, AY, and AX, and we use our usual method. So I'm taking moments about this point. Now I have all these forces here, and so what do I have? I've got 4.5 times 4. This one goes straight through, so it's don't have to consider it. I've got 3.53 times 3. 3.53 times 4. 0.553 C perpendicular times 4. 0.832 C perpendicular times 6. 6 times 3. And the directions, this is going to be clockwise, so it's positive. Counterclockwise, so it's negative. Clockwise, so it's positive. Counterclockwise, so it's negative. Counterclockwise, so it's negative. Clockwise, so it's positive. I put all of those into here. I solve for C perpendicular. I get that. Then I can take, now interestingly enough, I can take moments about point D. Now why am I going to take moments about point D? Well, I want to take, I know what C perpendicular is, but I can take moments about any point here. If I want to get AX, so in other words, I want to get AX, I don't want to take moments about any point through which AX acts. So don't take moments, through which the line of action of AX acts. So you don't take any moments about any point like that to get AX. So I'm just choosing point D in a sense. It makes my equations a little bit easier because it eliminates all of these forces here, and it also eliminates AY. So I don't know what AY is, so it'd be nice not to have it into my equation. So I'm getting rid of a lot of these forces simply by choosing point D. So what we're going to learn as we go along here is that you're going to look at these trusses, and there are going to be times you're going to make your life a lot easier when you choose certain points to take moments about. So this is a little bit new. You're going to need to look for various points to take your moments about. Okay, so if I take moments about point D, I'm going to have, in my equation, I'll have AX, I'll have this 3.53, I'll have this one, and I'll have the 6. So I'm only going to have 4 terms in my equation. And so I'm going to have 3.53 times 3. I'm going to have the 0.832 C perpendicular times 6. I'm going to have this 6 times 3. And I'm going to have my AX times 4. In terms of the signs, this is clockwise, so it's positive. This is counterclockwise, so it's negative. This is clockwise, so it's positive. This is counterclockwise, so it's negative. I put all those things in here. Now I've already solved for C perpendicular, so I just substitute it. So I use my picture correctly. I substitute in the 4.51 here, and now I can solve for AX. It's 1.52. And now I can take, I'm doing this with moments. I'm showing how we can do this all with moments. And now I'm going to take moments about point C. My only unknown left is AY. So taking moments about point C, again, I eliminate a number of forces here. So it simplifies my life a little bit. And I'm going to have 5.36 times 6, the 3.53 times 3, the 6 times 3, the AX times 4, and the AY times 6. In terms of the signs, counterclockwise, so it's negative. Counterclockwise, so it's negative. Counterclockwise, so it's negative. Counterclockwise, so it's negative. Clockwise, so it's positive. All those go into there. And I saw, then, okay, what do I know? I know I found AX, it's 1.52. And so I substitute that 1.52 into there. And I get AY is 11.14. So I draw my final free body diagram. All of them are positive, so I don't have to switch any arrows around. And I can do a check. Does my right, this is a good check because I used the moment equation 3 times here. So if I just take this sum of the right equaling sum of the left, they do 6.02, 6.02. Up and down are the same. 14.89, 14.89. So that's a good check because I used the moment equation 3 times. I can now use the sum of the forces in the x and y direction. So again, not guaranteed to be exactly right, but or not guaranteed that you're going to have the exactly right answer, but it gives you more confidence when that all is true. So, and then I'll just note at the end we have C perpendicular is 4.51. Well, I can then substitute in that value into there, and I can get my actual numbers there of 2.5 kilonewtons and 3.75 kilonewtons. So just plug those in. Okay, so here's a homework problem for you. I see now that this is not in an x and y angle, so what you need to do is you need to put the force perpendicular there, but then you need to get this angle, and the way to get that is to draw a triangle out in here. That's one way to do it. Okay, so work this one. Okay, so we've drawn this triangle here. Purpose is I want to get this angle with respect to the x-axis, and that would, so what do I know? This angle and this angle are the same. So this is, we call it 90 minus theta, we call it beta, whatever. But this angle, if this angle is theta, this angle is going to be 90 minus theta, and then this angle is also 90 minus theta. So how can I get this angle theta? Well, this angle theta is, we can make another triangle here which looks like that, and so I know that the tangent of theta is this distance over this distance. So the tangent of theta, this is 5, this is 6, so so theta is equal to the arc tangent of 5 over 6. And that is 39.8. That means that 90 minus theta is 50.2, which means that the angle with respect to the x-axis here is 50.2 degrees. So, now that we've done this so many times, I'm not going to dwell on it, but this goes upward to the right. So we have upward to the right. This one goes downward to the left. So we have downward to the left. And so this is sine of 50.2 times b perpendicular. Like I say, we're going to call this force b perpendicular. It's a point B. It's perpendicular to that. And this is cosine 50.2, so it's 0.64 b perpendicular. this is 8 kips sine 70 degrees. This is 8 kips cosine 70 degrees. So now we have our initial free body diagram, and I'm now going to take moments about A. So there's A. Notice that goes through the point, so we don't need to consider it. And so we have 0.64 be perpendicular times this distance. That's the line of action. We have 2.74 times that distance, same distance. We have the 0.768 be perpendicular times that distance. And we have the 12 kips times that distance. This one's going to be clockwise, so it's positive. Clockwise, positive. Counterclockwise, negative. Clockwise, positive. Put all that in there, solve. We get that value. Now we take moments. Now we're going to take moments about C. So I'm going to take moments about this point. Why do we do that? Because, well, okay, we solve for B perpendicular. We have that one. So I now have this. I have those two values. If I take moments about point C, notice what do I eliminate? I eliminate the AY. So I eliminate that one. And then I can solve for AX. So I'm going to have this force times that distance. This one goes through the point, so I don't need to consider it. I have this force times this distance. That distance there, so the same as that. And I have the AX times that distance. And what are the signs? Clockwise, positive. Clockwise, positive. Counterclockwise, negative. Put those all in here. I then, be perpendicular, I'm going to use that. Now notice this is a negative sign. We have to be true to our figure because we're using this figure. We don't flip the arrows around until the final free body diagram. So I have to use the negative 2.86. I have to put the negative 2.86 into that. Because I look at my figure and I'm true to the figure. I draw everything like that. So make sure that when you're doing this, like I say, we don't flip the arrows around till the final free body diagram. So I'm going to use that negative in here. So make sure you don't mess up the signs there. And then solve for AX, and that's what I get. Lastly, I can take moments about B. And so I take moments about this point. Why do I choose that? Because I'm trying to get AY now with a moment equation. And I can't choose point C to get AY because AY goes through that point. It's going to disappear from the equation. So I'm choosing point B, and that also gets rid of that force there. And so I do point B, and I have what? I've got 7.52 times that distance. I have 12 times that distance. I have AY times that distance. I have AX times that distance. And what are the signs? I'm going to have, this is going to be clockwise, so it's positive. Clockwise, so it's positive. Counterclockwise, so it's negative. Counterclockwise, so it's negative. Put all those values in there, I get AY. Here's my final free body diagram. Now notice I'm putting in my negative values up here, which means that what I've got to change the direction of the arrows. So I get the arrows going in that direction. I have to flip both of those, of course. And there's my final free body diagram. I do a check. Up forces equal down forces. Forces to the right equals forces to the left. We have OK. Okay, I'll stop there.